Okay, in this video we're going to talk about similarity. Similarity is a relation between matrices. In geometry you've talked about similar geometrical figures, similar triangles. So these similar triangles are not identical, but they have something in common. They have the same shape, so to speak. And in the same way, we have similar matrices have the same quote shape. Now we've already seen something like this when we went back to when we were talking about homomorphisms. We showed that a single homomorphism or linear transformation has different representations when you choose different bases for the domain and for the codomain. And all of these matrices are related in some way. And we did show that it's possible always to choose two bases, B and D, such that the representation of that linear transformation with respect to these two matrices has this form. Okay. So in the current chapter, we're going to talk about the case where the domain and codomain bases are the same. So in fact, it's a mapping from a vector space to itself, and the domain and codomain bases are the same. And we'll find that we can't always represent in such a simple way, but we want to find a representation that makes the matrix as simple as possible. Okay, so let's go back to the presentation. Now in this investigation, we will have to factor polynomials. But you may remember from college algebra that you can't always factor polynomials with real roots. Here's one example. If we have x squared plus 1, you need imaginary roots in this case. So we're going to do a short review of complex numbers and factoring of polynomials. Okay, so if we have a polynomial where the leading coefficient Cn is not 0, then the degree of the polynomial is n. In other words, n is the power of x, the largest power of x, that has a non-zero coefficient. If n equals 0, then the polynomial is a constant polynomial, and constant polynomials we say have degree 0. And the zero polynomial is defined to have degree minus infinity. So there's the definition of degree. Now, just as integers have division, so we have polynomials. You've probably done long division with polynomials. Here's one example. If I divide 3x cubed plus 2x squared minus x plus 4 by x squared plus x, hopefully this algorithm is familiar to you. To find the first factor, we look at the leading factor in the denominator and the leading factor in the numerator, and we find, well, how many times will x squared go into 3x cubed, and you get 3x. And then you do the usual subtraction. You take 3x times x squared plus x, and you subtract that from the original numerator, and that gives me minus x squared plus x. So I do the same thing now. Notice how that x squared goes into minus x squared minus 1 time. So then I subtract minus 1 times x squared plus x. This is where it gets a little tricky because you're subtracting a negative number. So if I'm subtracting minus 1 times x squared plus x, it's going to be plus x squared plus x, and that gives me 0. Okay, so we can write this as this original polynomial, 3x cubed plus 2x squared minus x plus 4 is equal to x squared plus x times 3x squared minus 4. Okay. Yes, notice that there is a remainder 4 when you subtract this off. Okay, so hopefully you've seen this kind of division before. Okay, so some definitions. Just as when you're dividing with integers, you have a quotient and a remainder. So if I divide p by d, I have p is equal to d times the quotient plus the remainder. Now the degree of the remainder is going to be smaller, just as in this example, because every time you do a partial division, you're reducing the degree of the result. After I subtracted off 3x times x squared plus x, I got minus x squared minus x. The degree of this polynomial is smaller than the degree of this polynomial. And each step we're going to reduce the degree of what's left until we reach the remainder, which is going to have a smaller degree than the original polynomial. Okay. Now, corollary, the remainder when p of x is divided by x minus lambda is the constant polynomial r of x equals to p of lambda. Okay, and the proof of this, the remainder when p of x is divided by, all right, so the proof is just the same as the corollary. Let's stop for a moment and think why this is true. All right, here we have a little more detail. If we take this expression here, now this must be true for all x, so in particular it's true for lambda. So if I plug lambda in for x, I get this result. Now in the particular case when you're dividing by x minus lambda, this x minus lambda is your d of x. Now if d of x equals x minus lambda, then d of lambda is lambda minus lambda, which is equal to 0. So that gives me directly from this equation, p of lambda is equal to r of lambda. Now the final step is notice that r of lambda has a degree which is less than the degree of d of x. Now the degree of d of x is 1. So that means the degree of r must be 0. So r must be a constant, and r is equal to the polynomial p evaluated at lambda. Okay, so if a divisor d of x goes into the, so here we're going to repeat this. If divisor d of x goes into dividend evenly, means that r of x is the 0 polynomial, then d of x is called a factor of p of x. All right, just like with integers, if you can divide an integer evenly by another integer, then that second integer is called a factor. Any root of the factor, any lambda such that d of lambda is equal to 0, is a root of p of x, since p of lambda equals d of lambda times q of lambda equal to 0. Okay? So if lambda is a root of the polynomial p of x, then x minus lambda divides p of x evenly. Right? So you can just take this corollary, and if p of lambda is equal to 0, then that means that p of x is divided evenly by x minus lambda. Okay? Now these are effects that you may know, but it's nice to have a proof of them. Okay, so there's the proof written out. Right, now, let's think about cubics. Now you know the quadratic equation. You can find roots of a quadratic equation, and you know that you can have complex roots when the square root part is negative. And we have this general theorem for polynomials. Any constant or linear polynomial is irreducible over the reals. That means you can't factor it any farther. A quadratic polynomial is irreducible over the reals if and only if its discriminant is negative. Remember, the discriminant is b squared minus 4ac, and that comes into the quadratic formula. And we have no cubic or higher degree polynomial is irreducible over the reals. Now here, irreducible means it has polynomial factors. So any polynomial of degree 3 or higher has factors. However, that doesn't necessarily mean that it has real roots. Okay, I can give a very simple example. If I take x squared plus 1, well, I could take x squared plus 1 squared. Now, this is going to be a fourth degree polynomial, and it has roots I and minus I. Now, this fourth degree polynomial has polynomial factors, but it doesn't necessarily have real roots. So any polynomial with real coefficients can be factored into linear and irreducible quadratic polynomials. That factorization is unique. Any two factorizations have the same powers of the same factors. Okay, and the proof is you just keep on reducing till you get down to linear or quadratic polynomials. So x squared plus 1 has no real roots and doesn't factor over the real numbers. So the I is defined as a root of this equation, x squared plus 1 equal to 0. Now, if I is defined as a root, by using algebra, you'll also have that minus I as a root. This gives us the complex numbers, which is the set of all numbers of the form a plus bi. And I'm sure you've seen this polar form also, that you have a plus this is a plus bi, and this is the real axis, and this is the imaginary axis. Okay. Okay. So in the complex numbers, all quadratic polynomials factor. So in contrast with the reals, C has no irreducible quadratics. So in the complex numbers, in fact, all polynomials reduce to a product of linear polynomials. Okay. Okay. So polynomials with complex coefficients factor into linear polynomials with complex coefficients. The factorization is unique. Complex representations. You have complex number addition, you add the real part and the imaginary part. Complex number multiplication, you do, I like to say it's like Floy. The first is AC, the last is BD, but when you multiply the I times I, you get a negative. So the real part is AC minus BD. So that's the first and last, gives you AC minus BD. Then you have the outside, which is AD, and the inside, which is BC, and both of those multiply I. Now, when you do matrices, you're just doing the same thing, because when you do a matrix multiplication, you are multiplying and adding. So you can verify that this is true. For example, let's verify this one here, 9 plus 3i. That's the first row, second column. So I would take the first row here times the second column here. So let's try it. 2 minus I times 3 plus 3i. That would be the first product, and the second product is plus 1 plus I times 2. Okay. So let's use our Floy. This is going to be 2 times 3 is 6. Okay. Last is going to be minus I times 3i, so that's going to be plus 3. Okay. And then for the other one we have let's see if I did that right. So then we have the inside, we're going to have I times minus 3 and then here we're going to have I did the inside, so here's the outside is going to be plus 2 times 3, so that's plus 6. And then here we have 1 plus I times 2, which is going to be plus 2 plus I. So it looks like there's actually a mistake here. This is not going to be 9 plus 3i. We have 9 plus 2, which is 11. And then here we have 3i plus I, which is 4i. All right, so it looks like this is actually 11 plus 4i. So you would do all the other multiplications the same way. Let's check this last one and see if this one is correct. 5 plus 3i. This would be 3i minus 3. I'm sorry, that would be actually, that's 3i minus 3. And then we'd have plus 8. So in fact, this one is correct. But you could go through and verify all of these. There's no guarantees all of these are correct, but you can see the procedure for finding them. Okay. So the same things we did with real numbers, we'll do with complex numbers. Okay. So we can write the real number 1 as 1 plus 0i. So the standard basis that has first basis element 1 and then all zeros, I can write as 1 plus 0i, 0 plus 0i down to the bottom. And you can just replace a real number expression by that same real number plus 0i. That's a complex number expression. And that's it for this.